The Intelligent Transportation Project, developed by Integrated Media Systems Centers at USC, collects and stores and analyzes transportation sensor data from Los Angeles County road networks. This project is a collaborative effort between government, academia, and industry. IMSC has been working with the Los Angeles Metropolitan Transportation Authority for the past several years to collect and archive the road network sensor data using Microsoft tools. The traffic data types received from RITS, Regional Integrated Intelligent Transportation System, range from highway, arterial, bus and train GPS to ramp, meter, events, and CMS. Microsoft Stream Insight acquires and processes these datasets using input and output adapters. SI includes one input adapter for each data type and two output adapters to store the data in a cloud storage system, Windows Azure, and a local database server. On average, the system processes around 15 terabytes of data per year. Since 2010, the Clever Transportation Project at USC depicts traffic data for both highway and arterial data vectors in Los Angeles County on a Bing map. Scattered across 3,000 square miles, 6,500 large-scale and high-resolution traffic sensors relay information back to IMSC servers. The dataset includes real-time data at a sampling rate of 1 minute. However, for demo purposes, the data map is updated every 5 seconds. Each data point indicates the current speed of that sensor with a color code. Here is a highway map of Los Angeles with 2,000 sensors scattered across all the freeways. Data regarding speed, volume, and capacity are collected. Color codes indicate red as slower traffic and green as no traffic at all. Stream Insight input adapters receive data from RITS and run continuous queries outputting the results to graphs. We define a query once, and as the data comes in, the results are updated accordingly. On the right-hand side, there are 3 graphs representing the data. The uppermost graph shows the average speed of all the sensors in the last 60 minutes. In addition, it is possible to select a variable range for both space and time. The middle chart shows the average speed of all sensors for the past 24 hours. Using this graph, one can see the peak hours in traffic within a day. Lastly, the bottom graph depicts the relationship between volume and capacity for a specific traffic sensor. Moving on to the arterial sensors, there are 4,500 sensors installed across LA County, but here we show a subset on the map. When selecting the arterial data type, the graph changes immediately according to the new data. Similar to highway sensors, data regarding speed, volume, and capacity are relayed with the red and green color codes. For the arterial map, we have the option to select a range query. By selecting a range, the map automatically zooms in and shows the appropriate data graph on the right. Using high-resolution traffic sensor data stored in Microsoft Azure, we generate time-varying traffic patterns of Los Angeles highways and arterial streets. Particularly, we spatially and temporally aggregate the traffic sensor data by assigning interpolation points every 5 minutes. These points depict the travel times on the road segments. Here you see the time-dependent speed information of 2 highway road segments in Los Angeles. On the charts, the X and Y axis respectively display time and speed of corresponding segments. The traffic patterns are useful for analyzing road segments' performance and forecasting traffic information ahead of drivers. Based on generated traffic patterns from historical traffic datasets, we developed several road network algorithms such as time-dependent fastest path computation and k-nearest neighbor search. Opposed to existing route planning applications that assume constant travel time for each road segment, our time-dependent algorithms consider the travel times as a function of time. Now let's demonstrate our time-dependent fastest path algorithm on Bing Maps generated on traffic patterns. First, we select a source and a destination, then choose a departure time from the time slider below the map. The green path is Bing Maps route recommendation and the blue path is a result of our algorithm. There are 2 observations here. 1. As you can see, our path is different. 2. As we change our departure time by moving the time slider, our path suggestion and its cost change. However, the Bing Map suggestion remains the same. This is because of time-varying edge travel time patterns. Our algorithm not only considers the edge weight as a function of time, but also takes into account the edge cost by the time you arrive to the start of the edge. Let's try this with another source and destination pair. Now it's 7 a.m. The suggested route of both Bing Maps and our algorithm is the same. As we slide to 8:30 a.m., we hit rush hour and pick a different road. As we slide further, rush hour is over and we revert back to the original route. We note that the traffic patterns change over time as new real-time sensor readings arrive in the system. Here, we use Stream Insight to continuously update the travel time patterns. We monitor and instantaneously update more than 10,000 edges in the Los Angeles road network.